Record. Okay. So once again, good afternoon. And today we will be talking about the interpolation methods. So to quickly wrap up what we have seen so far, we began with trying to determine the minimum or maximum of a function. So we saw graphical methods and we divided them into two types. One is bracketing and one is open methods. Now, if the function given to us is a unimodal function, that means there exists only one minimum or one point which gives us a minimum functional value. Then we can find the minimum or the reduced interval of uncertainty by applying the one-dimensional search method. So we saw a number of them. To quickly remind you, it was unrestricted search, exhaustive search, dichotomous search, interval halving, Fibonacci search, and golden section method. So this is what we have seen so far. And today what we'll be doing is we will be basically looking at interpolation. Okay, so if you're reading other references, probably you may also, the other term is like the polynomial interpolation method, or parabolic interpolation, and so forth. So today we'll be looking at basically two methods. One is the quadratic interpolation and the cubic interpolation. Both of them fall under the umbrella of polynomial interpolation. So to put it in easy words, what we're trying to do is we are trying to actually take advantage of the structure of a quadratic function. So we're beginning with quadratic interpolation. Okay, so we know a quadratic interpolation is a function where the order is 2. Okay, so a quadratic, so if you look at the dotted line over here, let me bring my pen, not stamp. So if you look at the dotted line, this is assume our function f of x, okay, our actual function. And the black line is our quadratic function, which we are interpolating it, and we call it q. Okay, so q is the quadratic interpolant of the function f. So the function f is given within some bound, let's say from x0 to x2. So these are the bounds. And so what happens is that if we have a quadratic function that can pass through these 2 points, okay, so we can say that the optimal, now over here we are looking at the maximum. You could have done it, inverted the figures, and it would have been the minimum. Okay, so the maximum of the quadratic function, which would be this blue point, would be an approximate of the maximum of the actual true f function. Okay, so by using interpolation, polynomial interpolation, we try to approximate the optimal point by using a quadratic or cubic interpolant. Okay, basically now let's look at the different types of quadratic interpolation and how it can be done. Okay, so basically there are three types of three methods of quadratic interpolation. Okay, so we'll be looking at all three of them, three different versions we can say, and it doesn't matter which one you use. In terms of convergence, well, the last one, the one where you have 3-point interpolation method is better, but you can also use 2-point interpolation methods. So now let's look at what it means. So there are three types. So there are two types. Two out of these three types require 2 points. That means you interpolate the function f at 2 points only. That means if I go back to this figure, I only need 2 points, let's say this point and this point, in order to approximate the function f. Okay, so there are two methods that can do that using only 2 points. And there's one method that can interpolate the function f using 3 points. So we have 1, 2, and 3 points. So depending on which one you use, the equations that will be involved are different. Okay, so now let's look at each of them. Let's begin with the 2-point interpolation. So we call this method 1. So the method 1 is a method of quadratic interpolation where we require only 2 points. So we know that the quadratic equation has this form. Is there anyone who doesn't know that the quadratic equation has this form? So it is of power 2. So ax squared plus bx plus c, where a, b, c are real values, and x is order 2. Okay. So assume that over here we have the brackets. That means we are given a function. Let me quickly draw over here. Suppose we are given some unimodal function, and let's say this point over here is x1. So we're given the bracket, and this point is, if you draw it, would be x2. Okay, so the bracket is given. So in this case, instead of xs and xf, we are using x1 and x2. Okay, so we are given a bracket which defines our unimodal function. So what you have to do is, and you're given the quadratic function that you want to use to interpolate your function f. Okay, so what you do is you have x1, x2. So basically, if you have x1, x2, and you have the function f, you can definitely evaluate f of x1. You can find f of x2, right? Now, what happens if I put, instead of x, x1? So I find the functional value we find the functional value at point x1. So it would be, instead of this, what I do is I put f of x1. So f of x1 is some value that I'll get. It will be some number. So I have some number, it is known. Then instead of x, I put x1, and I get an equation. So I call this equation, let's say, define. This, I put a triangle above. This means I define this whole equation as qx1. That means it is a quadratic function at point x1. Okay. Similarly, I have the other endpoint, which is x2. So if I evaluate the functional value, it will give me f of x2, which is some known value. And I will get a second quadratic equation. And I call this guy q of x2. Okay. Now I have 2 points. Pay attention over here that in a quadratic equation, you have 3 coefficients, A, B, and C. So basically what we want to do is we want to solve this system of equations, but we have 3 unknowns, which are A, B, and C, and we want to find them, right? F of x1 is known to us. We know how to find it because we know x1 and x2, and we know the function. F of x2 is known to us. And we have the quadratic equations, but we have 3 unknowns, A, B, C. So we need 3 equations. Am I right? Is it clear, guys?
Yes.
Okay. So we need 1 more equation. And how you can do that? Well, very easy. You can either find the derivative at this point or the derivative at this point. It doesn't matter. Okay, because we know this function, so we take the derivative. Over here, I've taken the derivative at point x, at the point x1. So if I take the derivative of this with respect to x1, it would give me this equation, and I know the derivative. I can calculate it. It would be some constant, and it would give me my third equation, which I call q prime x1. So now I have 3 equations and 3 unknowns, which are A, B, C. So we all know how to solve a system of 3 equations and 3 unknowns. So just for the sake of simplicity, if I replace like f of x1 with f of 1, just to make it easier, and f of x2 with f of 2. Okay, so this guy, this is this guy, and f prime x1 with f prime 1. Okay, just to make our equations look more beautiful. So if I do that, then, and I solve these equations, you can do that. You can try it at home, and you will see that you will eventually get A and B as shown over here. Okay, so we get 2 systems, A and B. All right. Is it clear?
Yes.
Good. Now, we want to find the minimum of the function q, right? We want to find the minimum of this function q. How do you do that? You do that by taking the derivative and equating it to 0. We know that to be a local minimum, this guy, the derivative should be equal to 0, okay? So doing that, it would give you minus b divided by 2a, okay? Now, substituting that, okay, so from this equation, where is it? From this equation, we have a, b. So substituting it over here, we would get the x minimum, which would be this function. All right, let me clear this for you. So basically now you would get the x minimum, which we are looking for, and it would be equal to equation 1.3, which is in terms of course, the first derivative and the functional values of f1 and f2, okay? So now if this is this point, so our new point is equal to our previous points, okay? So now you have to iterate. Okay, so now we found a new point, and then we have to use the elimination method to eliminate some part of the region of the interval. So what we can do is we can write this in an iterative manner. So we can say this new point is equal to the previous point minus the other point. So x1, x2 are, we can write 1 as k minus 1, 2 as k, okay, because x1 is less than x2. And x1 obviously will be again be k minus 1, and this guy would be k plus 1. So our new point in every iteration would be based on the previous 2 points that we have. And we see in the beginning, the 2 points would be the end points of our interval. So basically, in general, the iterative function of our first method of quadratic interpolation would be this. So all you have to do is just implement this, and you have to keep doing this until the functional value of f of x plus, f of x of k plus 1 minus f of x of k minus 1 or k is very, very small. Okay, so we keep doing this and we compare it with these 2 points, and based on the elimination method, we eliminate the region that we want. Okay, is it clear? It's very simple.
Yep.
Good. So in my notes, I have written quadratic interpolation. Well, I've used the Lagrange the equation over there, but we'll get to that. Don't worry. Another thing that I need to tell you, I was asked through an email, is yes, the exam, your exams would be open book, okay, and you can use whatever reference you want. So because it's online, and I do not know whether, even if I don't tell you, probably some of you would be opening your books and lecture notes. So to make it easy and make it fair, everyone can use whatever they want. But on the other side, it means that the questions would be something that you won't find anywhere, not even on the internet. So you will have to think about it. Okay. With that said, so the reason why I said this is because you do not need to learn these equations by heart. Okay, so you do not know to mug it up and say, okay, this is method 1, this is the equation, I have to learn it. I made a mistake in the plus and minus. So you have the book, you just open it, you just plug in the values, and you should get your answers. Okay. Now let's move to method 2. So any questions about method 1? No questions, method 1?
No.
Good. Now, so basically now in method 1, we saw that what we did is we took the functional values at the endpoints x1 and x2, and we took the derivative at x1, right? Now what we do over here is just the same, okay? But instead what we do is we just take, so you can also use this method, doesn't matter. You only take the functional value at 1 point, okay? So we know this is as before. And we take the derivative at 1 point, this was also as before, but we do not take the function value at x2. Instead, we take the derivative of the functional value at x2. Okay, so basically, instead of having two equations with 2 functional values and 1 derivative, we have an equation with 1 functional value and 2 derivatives. So you take the derivatives at the endpoints. Is it clear? So with this minor change, basically what you do is you just repeat, or you just do the same as we did earlier. So then based on that, you solve for A, B, and C. You have a system of 3 unknowns and 3 equations. You solve it, you would get X minimum in terms of X1, X2, and F1 prime and F2 prime. Okay, so basically over here, you get everything in terms of the derivatives, which unlike our previous case, where is it? Where is the minimum? Yes, sir. Here we have F1, F2, and we have the derivative. Yes, sir.
How we can ensure that the concave of our quadratic function would be the same as our initial function? Because
there is no guarantee that it would be the same. I'm not saying that they are the same. I'm saying it's very close. The only reason why
because since we are taking only 2 points, it can be like concave up, even like flipped to the other side.
Well, we assume that they are in the same direction. We use a function where it's in the same direction as the unimodal function. But all we have to ensure in a quadratic interpolation is that it, well, in these 2 methods that I'm telling you, it passes to 2 points. Okay. And
yes,
now
it can pass these 2 points, but concave up.
I know. So you're saying it's just the opposite of that.
Yes, yes.
Yes, I understand. So we assume that we know that it's not the opposite, it's in the same direction. So we choose a function which is, so we choose like A, B, C values, which would be in the same direction as our unimodal function. Okay.
But we are not like making any constraints to that. We are just finding A and B.
Yes, you're finding A and B in order to find this point. So what I'm saying is we assume that we know the direction, and if this is convex, then this will be convex. If this is concave, this will be concave. Okay. So what I understand what you're saying. We have 2 points. What happens that if we have it the other way direction? So if you have it the other way, so that function, we would not consider it. Okay, so if you're looking at unimodal, we'll have only functions. We look at quadratic functions, which will only be in that direction.
Okay.
Okay, so basically, so you do the same thing. You find x min in method 2, and you write it in an iterative or recursive manner, which would be this. And therefore, based on the same approach, you can keep doing this until and you can remove or eliminate the region that is not necessary based on the elimination method. And you keep doing this until you get a very small value of if the functional difference between the 2 points is very, very less than some epsilon. Okay. This is method, oops, this is, I'm sorry, method 1. No, sorry, method 2. I'm talking about method 2. So I'm sorry, for method 2, this would be the recursive equation, okay? So over here, what we have, you see we have everything in terms of the derivative only, all right? Now let's look at method 3. So the method 3, unlike method 1 and method 2, where we need only 2 points, over here we come up with 3 points. So we need 3 points, okay? So we have to choose 3 points, and based on that, we bracket our critical point, and we keep doing this iteration. Now, if I give you 2 points in the exam or quiz and I ask you to use method 3, basically what you have to do is, please don't be very confused. It's very easy. Just take the mid of these 2 points. It will be a 3rd point for you. So be creative. Don't think that the question is wrong. And I don't know, something else, you are mistaken something. No. If I ask you to use a 3-point method to interpolate a given function, and I only give you the interval, that means 2 points, just take the mid of the interval. That would give you 0.3, okay? And so basically, this is what you do. So instead of 2 points, you have 3 points. So when you have 3 points, when you ensure that your interpolant passes through 3 points or intersects the function f at 3 points, it means that it would be much closer, or the curve would be much more similar to that of the function f, okay? So over here, what we do is we use a formula called the Lagrange interpolation formula. Again, you don't have to learn this by heart, but this is the formula. So your Lagrange interpolation formula would be gives your interpolant function, the quadratic function that you are using, would be of this form, where you have 3 points, x1, x2, and x3. Again, f1, f2, f3 are the functional values at these 3 points, okay? So in order to find the minimum of this, you have to take the derivative of this and equate it to 0. So you can do this at home. So take the derivative of this with respect to x and equate it to 0. So it will give you some x min value, which would be this function, okay? And again, you can write this in an iterative manner as such. So this new function would be in terms of the previous 3 functions, which is x1, x2, and x3. So x1 would be k minus 1, x2, which is a midpoint, would be xk, and x3 would be xk plus 1, and this guy would be xk plus 2. So you get a new point based on the previous 3 points, and you keep doing this until you reach some tolerance, okay? Is it clear, guys? Yes or no?
Yes.
Because in the end, I will ask questions, and I do not want you to tell me I did not study, okay? So be very attentive. One more thing. So as I told over here, you have find the next point, and based on that, you decide on how to discard some part of the interval. Well, the thing over here is that you cannot use the same approach as you have used in method 1 and 2 or the elimination method. It's a bit more complicated. So if this point, so basically let me draw it over here. So if we have our function somewhere like this, so we have points x1, this is x2, I'm sorry, x3, which is the endpoints, and we say that we have taken the midpoint as x2, okay? And now we find a new point, x min, okay? Now it says that if x min lies between x1 and x3, so what we have to do is, obviously we have to compare x min with x2, right? So if we know that this point is a unimodal function, so obviously x min will lie in this function, in this interval. And so we have to compare it with x2. So if the distance between these 2 points, that means x min and x2 is very, very small, okay, then it means that we are done. That means if you take the functional value, obviously that will be very close as well. But if they are not very, if the distance between x min that you have found and x2 is not very small, then you have 4 cases that you have to compare. So your new set of 3 points for the next iteration, which I call x1, x2, x3 new, would be based on this comparison. Okay, so now let's say x4 over here is my x min. Okay, so let's say x4 because I took this from my notes, and so x4 is basically the same as x min that we have used over here. So now, so our new set of points for the next iteration would be x1, x2, and some x4. So obviously x4 would be between x2 and x3. If x4 is after x2, that means x4 is greater than x2, and the functional value of x4 is greater than function value of x2. That's obvious. That means if we have something like this. So if we say this is x4 or x min, okay, you see that the functional value of this guy is greater than the functional value of this guy. So obviously the minimum point would be in this bracket and not, so we can discard x4 to x3. All right. So that is this case. So that would make my new set of points as x1, x2, and x4. Now, let us...
Sorry, may I ask a question?
You may, sir.
Here, F2 and in the previous slide, F1, F3, they are all functional values at which, like f of x1, f of x2, f of x3, yes? It gives the number.
X1 is the point, the points on the x-axis, and f of x2 is the functional value of x2. So f2 means function value of f of x2. This point, that means on the y.
In the previous slide?
In the previous slide, yes, here.
Here, in the middle, x
here.
Min, yes, x min gives us a number then?
Yes, x min will give you a point. It will give you a point on the x-axis, 1 point over here. Okay?
Yes, but also the qx also would give us a number then.
Yes, but we are finding the minimum of it. So how do you find the minimum? You take the derivative of qx with respect to x and equal to 0. That's what I have written. To find the minimum, of course, we take the derivative of, this is 1.8, not 2.8. 1.8
okay, I get it.
And set it to 0. Okay?
Mm-hmm.
Is it clear?
Yes, yes.
Okay, good. So going back over here, oh, we have to draw that guy again. Let's say x1, x3, and midpoint x2. Remember, x2 need not be the midpoint, but just for the sake of simplicity, I've taken it. So we understood case 1. Is there anyone who did not understand the case 1? Case 2. Now we say that our new interval on the new 3 points would be x2, x4, and x3. That means obviously x4 is again over here. So it would be this bracket, okay? If obviously x4 is greater than, this is x4. Greater than x2, yes it is, and the functional value of x4 is less than x2. That means we have some function like this. The functional value of this guy is greater than this guy. So that's why we can discard this area. So we can say these are our new points. Okay, so that is case 2. Clear?
Yep.
Good. How do we erase? I want to erase on this and this. Okay. Now our third case is that we take x. Oh, sorry, it's x2. We take x4, x2, and x3. So obviously x4 is somewhere over here. And that is if x4 is less than x2 and the functional value of x4 is greater than x2. So obviously it is something like this. So x4 is greater than x2. So therefore we can discard this guy and our new points would be x4, x2, and x3. Okay, and we put it in our equation on slide 7 and we iterate over it. So that's case 3. And our final case is when x1, x4, x2. So x1, obviously x4 is somewhere over here again, and x2. And that is when x4 is less than x2, which is true, and function value of x4 is less than. So we have some function like this. This functional value is less than this functional value, so we can discard this guy. And therefore, these 3 would be our point for the next iteration. So is it clear, everyone?
Yes.
This point x4 is like chosen randomly.
My dear, no, x4 is this guy. I mentioned x4 is x min. Guys, x min
okay,
that I
okay,
get here is the same as x4. As you see over here, I have added it. So just for the first round, I have written it as x4, x1, x2. Remember? I had written it over here. Let me write it once again, guys. In this example, what I've written over here, x4 is the same as x min that we got, okay? All right?
Yes.
Good. Okay, any questions so far? Good. Now, next I have given you an example. I've given you a, let me clear this. I've given you an example and I see I've used new terms, parabolic interpolation to approximate. So parabolic means the same as quadratic, okay? Because a parabola is also a function of order 2. So I've given you a function and I want you to approximate this. I've given you a function f of x and I want you to use quadratic interpolation to approximate this function. And the guessing points are, I've given you the 3 points. So that means I'm telling you, you have to use the 3-point method, okay? x1, x2, 0, x0, x1, and x2, okay? So basically what you have to do is solve it, find the function, put it in the Lagrangian interpolation formula, evaluate it, and then you see whether discard the interval based on this, and you iterate until you get some very small value. So I keep doing this, as you see over here, like when I get to the 5th iteration, okay, I see that my f of x0, f of x1, and f of x2 are very close. And therefore, our new point is also very close to the previous point. So when I compare them, I would see like if I compare f of x3 to f of x1 and f of x0, I see that they are almost the same. So that means I get to the true value, which is equal to 1.755. So x value would be equal to 1276. Where is it? 1276, this guy. Okay, is it clear? So you iterate it and you just work out this, you put it in the Lagrangian formula and you would get this. So I'm using the 3-point method. I will share the slides with you, so do not worry. Any questions before we move on to our cubic? No questions, guys? Do you want me to ask you a question?
No question.
Okay, good. Now, to understand the cubic, basically, again, the slide that I have provided over here. Okay, so this is polynomial. So you see over here, I've written an equation which is fancy, and actually this is in your textbook. And I believe like it may not be easy to follow. If those of you have followed it, very good, well done. But if not, then you can just look at my slides. I've tried to make it easy. I think that's much more easy. And this is the 4 cases that I copied from my notes. Now we go to cubic interpolation. Again, over here, it is very fancy. There are 2 cases and blah, blah, blah. How did I get this? This makes no sense. forget about this and listen to what I'm going to tell you. And I will show you that how I can get to this equation, okay, in a much more easier manner, okay? To do that, I need MS Paint. Okay. So now we're going to study about cubic interpolation method. So the cubic interpolation obviously is much better than the quadratic or any of the line search methods that we have seen so far. But of course, in terms of computation, it takes more time, it's more complex. And in cubic interpolation method, what we need is what is it? 4 equations, okay? So in my notes, I've used a 2-point method. That means I've given 2 points. How can I obtain the 4 equations? Okay, so I need 4 unknowns and 4 equations, but given 2 points. So basically what we have is, I know that we can draw a line. Let's control Z, undo. Where's undo? There should be undo. So let's say we have a line. Okay, so in interpolation, cubic interpolation method, what we are going to do is we are going to use 4 equations. So we have to come up with 4 equations. So if we have, I don't know. What am I doing? It's not easy. Now, if we have a function, what I want is I want 2 points, which is my x1 and x2, basically my my intervals. Let's call it x1 and x2. Okay, so what I want to do now is I want to actually I can write text. Minimize f of x, which is that red function that I've written, such that x lies in the interval x1 to x2. Okay, is it clear? So this is what I want to do. Now, what we are going to use is going to use a cubic function. A cubic function is a 3rd-degree polynomial. So a 3rd-degree polynomial, you guys know what it is, right? Is there anyone who doesn't know what a 3rd-degree polynomial is? Let me write it for you. So we can write it in terms of, let's say, polynomial. Let's say we have a0 plus a1 times, this is a different way of writing a polynomial equation, and I'll tell you how we got this. If anyone knows how we got this, then that's good. Actually, I'm going to ask you how we got this. x1, so I can write it to the power 2 plus a3 times x minus x1, oops, to the power 3. Okay. Some of you may say, okay, why didn't you write, I don't know, a0 plus a1x plus a2x squared plus a3x cubed? You could do that, but in order to get those equations that I have in my notes, you can also write a cubic cubic function in this form. Okay, and how do we get this? Anyone can tell me? Okay, let me ask, because today we have less number of attendants. Adil, can you tell me why I can write it in this form? Mr. Adil Kuterbayev. Okay, Ainur, please keep note of the students who are not answering, because I'm not sure whether they are even here. Let's see, Aigerim. Aigerim Gilmanova. Okay, Aigerim as well. Asad.
Yeah, Professor.
What's your excuse? I hope you can answer my question. Otherwise, I will be very sad.
Yes, I'm here.
How is it? How did I get this equation for a cubic function? How can I? Is it true? I mean, I know it's true that I can write it like this, but where did I get this from?
Did you ask about this about x minus x minus 1?
Yes.
I think,
yes.
We each function, if we write in the form of a0 plus a1 x plus a2x squared and other, we assume that this function is symmetrical regarding the y-axis, but each function could be also be shifted regarding the y and x axis. Therefore, we should mention it in our polynomial equation. Is it right?
That's not what I asked. I asked you where did this x minus x1 come from? Why is it that I can write a cubic function in this form? Is it correct that I can write it in this form where x1 is this point and x? Why is it? How did I get this equation? That's my question.
Really good.
What is a Taylor expansion? I know, so I'm given a function f of x. Okay.
Yep.
And I'm given the functional value at some point a. So the Taylor series, we talked about this. Taylor series would be f of, let's say, a
plus f derivative of
f of a divided by 1 factorial times x minus a plus.
Yeah. It's infinite sequences. Second
Yes,
derivative.
but are you trying to compare? Do you see the similarity between what I'm writing now and the equation above for px?
Yeah, I see the pattern, but
yes.
I could not explain it.
So I have to write one more, which is f of 3 of a. That means the third derivative of f of a, assuming that the function is n-time differentiable, times x minus a to the power 3. Now, if you look at this, so I can write a function or I can approximate a function using this. So if the more number of terms I have, the more accurate this evaluation would be. So I know the functional value at some point a. Okay, so I can use that. So basically, this would be my a naught. Is everyone following? This guy. This would again be, I know the functional value at point a, I know the derivative, and so this would be also some constant value, and this I can call a1. And this guy is this guy. Because I know the functional value of x1, I'm given x1, I want to find it at f of x, which is p of x in here, okay? So this guy is the same as writing x minus x1, where a is equal to x1. Again, over here, I have this is a constant, and this would be a2. This is again x minus x1 to the power 2, same as this guy. And this again would be a3, which is this guy. So now do you understand how I got this equation, everyone?
Yeah.
Good.
Yes.
So using Taylor expansion, you can actually write this. So now I can say that, okay, so the cubic function that I want to use or to interpolate this function f of x, which is a red line over here, is p of x. And I get it by writing the Taylor's expansion for that up till the term, the fourth term, which is of order 3. Okay. So once we have this, then the rest is very easy. Now, I told you I've given 2 points, but I need 4 equations. So obviously, it's very easy to say what it would be, how we can do that. So the 2 points are given to us. So if 2 points x1 and x2 are given to us, okay, we know that we can find the functional value of these 2 points, which would be of f of x1 and f of x2. Okay. And we know that, therefore, if we have the functional value, we also know that we can find the first derivative of these 2 guys, these 2 points. So is it clear? Yes?
Yes.
Okay.
Yes.
So I've already got my 4 equations now. I've got the functional values at the points, and I've got the first derivative at those points. So basically what I can write is P of, let me type it for you guys. Let me erase this so that you guys don't get confused. And now let's type it like above. So P of x1 would be the same as f of x1, which I have written which is the same as f of 1. Okay, don't get confused. So this is one equation. So what means that in place of x, I plug in x1, okay, and I get the equation in terms of a0, a1, a2, a3, and we know the functional value of f of x1. We can calculate. So this will be some constant. Okay, so this is equation 1. Obviously, you can tell me what equation 2 is. Equation 2 would be P at point x2, which is equal to f of x2, right? Is it clear?
Yes.
Are this x1's same for px and
Yes, so I have x1 and x2. I've given you 2 points. Given 2 points and the function, I can find their functional values, right?
so f1 is a naught?
So F1 is, that means if I plug in, 1 minute. If I plug in, instead of X, if I put everywhere you see X, you put X1. We use a different color, okay? So this will become X1, and this will become X1. So as you said, this would become 0, 0, 0. So F of X1 would be equal to A0. Therefore, this first equation would be P of X1 is equal to f of 1, which is equal to a naught. So I have one equation, so I know that a naught would be equal to the functional value at the point x1. Clear?
Yeah.
Good. So let me finish writing this equations then. So I have 2 equations now. And now we write the third equation. So the first equation would give me a naught. Actually, guys, let me write it very clear. Let me type it down because I think it would be clearer for everyone to follow if I type. So I'm going to type what I just wrote. Okay, but first, let me first write the 3 or 4 equations that we get from the 2 points. Okay, and we go to this again. So our next 2 point equations would be p prime of x1. Okay, right? So this would be actually what? F prime of x1, right? And the next point, the next function would be p prime of obviously x2, which is equal to f prime of x2. So now I have my 3 equations. And now we see that how we can get the, based on these 3 equations, how we can find 3 equations in terms of a naught to a3. Okay, so the first one I told you would give us, let me draw it here. So I would get a naught is equal to f of 1, right? F of 1 means f of x1. Okay, I'm just simplifying it. So this would be, so if in place, so how do we get this? Wherever you see x in this equation, you just replace it with x1. Okay, so this is about this. Then our next, this guy would give us another equation. So from this, we get this equation. What do we get? Anyone? From P of x2. So that means in this equation, wherever there is x, you have to replace it with x2. So this would give me a naught plus a1 times x2 minus x1 plus a2. Correct me if I make any mistake, guys, because I am thinking and writing in real time. So it may occur that I make a mistake. So I'm just replacing x2 in place of x in this px formula. What else? We have to write one more, right? Let's put space so we know that we are writing how many terms we are actually including. Therefore, a3 correct? x2 minus x1 to the power 3. So what I did is in place of x, yes, sir. Did I make a mistake?
No, can we express the first formula where px, a basic formula of polynomial, can we express it in terms of x2 or any other point?
Yes, you can write it in terms of x2 also, given 2 points. So you can write this in terms of x minus x2. It doesn't matter.
Okay, so
Okay, I've just chosen x1 because I don't know, because it's just x1. Normally you choose x1 just for the sake of simplicity. And from this, I want to actually get to this strange equations that I have over here, these two. So that's why I'm just working it out till we get there. It doesn't matter. You can use x2, any 2 point, any one of the 2 points given to you. Okay.
can we express in terms of any point lying between x1 and x2?
Yes, any point also lying between x1 and x2. But since I've given you, question is the problem statement said you're given 2 points, x1 and x2. So why would we choose any other point? Okay, because we know it's a unimodal function, the minimum point will be somewhere here. So we are trying to find the functional value at any point that we know. At any point that you take in between, we do not know what the functional value is, right? We only know these 2 points because they are given to you and the functional values can be obtained. Okay.
Okay, thanks.
Okay, so that leaves us with 2 more functions. So we found 2 functions, 3. Yeah. So the third function would be from this guy. So that means the first derivative of the function at point x1. So if I take the first derivative, what would be the first derivative? So I take the derivative of this guy. What is the derivative of this guy? Anyone? What is the derivative of p prime of x?
A1.
A1
A1 plus
plus 2
2A2
A2 times
x
X minus x.
x minus x1. Good.
1
Plus
3 times.
3A3
3A3
x minus
Times.
1 squared.
x minus x1 to the power 2. Am I right? Oops, forgive me.
Yep.
Okay, how do we select? Does it select this guy again? Okay.
No, you cannot.
You cannot?
No,
Interesting. Okay, this is a continuation of that. I'm sorry about that. Okay.
You can cut and paste it.
Yes.
Huh?
You can cut and
use
paste it.
select tool.
X1 squared. You can cut it
Select.
and then replace it. Yes,
I
yes.
select
X1
this.
squared. No,
No,
only
no.
X1 squared.
Okay. I only select x.
Only X1 squared and then replace it to the.
Interesting. Okay, so Control Z again. I'm sorry because I've never used this thing before. Control V.
I think you can use arrow buttons.
You can use arrow. Where is arrow? My goodness, I am terrible.
On your keyboard. Buttons.
1 minute. Where did I? Okay. Oh, I have to do this.
You can
you
make
can
it
scale
bigger
it
and then move
yeah.
and then make it smaller.
Oh my God, this is terrible. Jesus. Okay, let's just be patient. Okay, so this is what I want to do, okay? So this is x minus of x1 whole square, okay? Now, that's the derivative, and now what I want to do is in place of this, wherever I see x, I put x1. So what would this function give me? Guys, read it out to me quickly because we are running out of time. So this would be basically A1, right? Is equal to F1. Am I right? F prime of 1. Correct?
Yes.
This will go off, this will go off.
Yes.
We'll get F1 and we have this guy. Good. And the final thing that we have is the equation that this guy would give us. And that would be from P prime of x2. So this would give me A1. Please correct me if I'm wrong, guys. 2 times A2 x2, I'm replacing x2, I'm sorry, x1. This will be 3a3 times x2 minus x1 to the power 2. Correct?
Yes.
Yes, yes.
Good. So now I have my 3 equations, and I'm sorry, I have my 4 equations and the 4 unknowns, which is a0, a1, a2, a3. So now we know, okay, can I scroll down? Does this go down? No. So now I know, I'll write it over here. So I know that the necessary condition for an octave, so to find, where is my, okay.
Can zoom out and track the bottom line
Ah, good,
and
smart.
track.
Good, thank you. Well, I want to write here now. So I have, we know that, okay, not red. I don't like red very much. The necessary condition for an optimal minimum point would be that P, the first derivative of P at some point, say X star, should be equal to 0. Am I right?
Yes, yes.
Okay. So that means if we want to do that, what we have to do is we have to take okay, this is a necessary condition, and we have the sufficient condition. Sufficient condition was that the second derivative of P at this point X star should be greater than 0 for it to be a minimum, okay? So we are assuming it's a minimum. So we have these 2 conditions, okay? So basically what we have to do now is we have to, so from these 4 equations, we have to find A1, A2, A3, A0, A1, A2, and A3. We can find it, okay? So that is there. Now, once we know that A1, A0, A1, A2, A3, okay? Now we know that to find the local minimum, we take the first derivative at some point x0, and this should be equal to 0. So for that to happen, let's write it here. So basically, I want a pen. Okay, so this I'm going to write over here now. So it means that A1, correct me if I'm wrong, 2 times A2 times x0 minus x1 plus 3a3 times x0 minus x1 to the power 2 is equal to 0. So this is a quadratic equation, and we know how to solve a quadratic equation, right? Everyone?
Yes.
Yes.
Yes, so we know how to solve a quadratic equation. So if you solve this guy, it would give you 2 solutions, okay? So let me write you the 2 solutions for this. So this guy would give us 2 solutions. And these are the 2 solutions under 2 conditions. So I'm sorry. This is 1. I make it big so that we can fit it in. So x star would be equal to x1 plus, how do we divide over here? Okay, I'll put it in brackets. Divided by 3. I have worked this out. Oh, sorry. I have worked this out before, so I am writing it down. 3 times a3. Okay, so this is 3 multiplied by a3. Let me write multiply with, this will be an x again. So let's say dot. Okay, so 3 dot a3 means 3 times a3, and in the numerator, what we would have, minus a2 plus square root of a2 square minus 3 times dot 3 times a1 dot a3. Okay, so this would be in the numerator, and x star, the second case would be, second solution, x1 minus a1 divided by 2 times a2. Okay, now what is the difference between these 2? So this first one is a solution when A3, I'm sorry, A3 is not equal to 0 because we have A3 in the denominator, okay? And this is the solution when A3 is equal to 0. So basically, to make this to merge these two solutions into one, what we can do is we can multiply this first solution, multiply and divide the first solution by this term, which is a square root term. Instead of minus, you put the plus term, okay? So you multiply, divide by that. So these two equations can basically be written in one form. X star is equal to, let me see. I don't want to make a mistake. X1 plus minus A1 divided by whole A2 plus square root of A2 to the power 2. So this is inside the square root, right? Minus of 3 if I multiply times A1 times A3. Is it clear? So basically, this, if I want to write it with my hand, this would be x cube. X star is equal to x1 plus minus A1 divided by A2 plus square root of A2 square minus 3 A1 times A3. So now even if A3 is equal to 0, this would give you this equation over here. Okay, so this is the overall equation. Now, if you go back to my lecture notes, and basically, if you just look at these two equations, these are the two solutions. And if you plug in the values, you will see that this is exactly the same. So A over here is the same as A1. The first derivative at point x1 is A3. And we know that, where is it? So when you solve for these two equations, you will see that actually the A3 that you get over here would be the first derivative at point x1, okay? And B over here would be equal, so B over here is equal to A2, okay? And you just plug in, you would see that this equation is the same. So you get one equation. So these two equations are given here. And to make them equal to 1, I've just given you one whole equation. So this equation would be basically the equation that you get to find a new point, which is the x star or x4 if you want to call it. Sorry, we have x1 and x2, so you can call it x3. And again, you iterate it, and you eliminate the interval that you do not need, discard it, because you have 2 points, so you can use the elimination method, and you find your new point every time. So is it clear? Any questions? So this is the cubic interpolation. So you can just forget my notes, forget this, because this uses a different technique and that is more complicated. So you don't have to consider this, just consider what I told you today. And using just these 4 equations, you can find A0, A1, A2, and A3. And your final point would be, your new point would be x star, which would be in terms of x1 and the values of A1, A2, A3. Okay. So I will give you some exercises to work on it with solutions so you can understand how it works. Okay. Any questions?
Sorry, in each iteration, what will be changed?
So in the iteration, what you have is you have a new point, okay, and you compare this new point. So you will have a new point between x1 and x2. So you will have, like, say, this will be your x star, right? So now you have 3 points you compare what the functional value at these points. We have seen the elimination method, right? In the elimination method, you have to now find, so for example, if this is the new x star, but this is the minimum point. So you know the functional value at this point is less than the functional value at this point. So you can discard this. So now your new interval will be x1 and x star, okay? You repeat this whole technique, okay? And then again, you'll find another new x star over here. So this x star would become your new x2, let's call it x2 prime. And then again, you repeat till you find a new x star between x1 and x2 prime, and you keep doing that till you get to a closer point. So every time you're reducing the interval till you get to the actual minimum point. Okay?
Okay. Thank you.
Good. Well, good. If you have no questions, we will meet on Tuesday. On Tuesday, you will have a quiz, by the way, till the end of cubic interpolation. It will be open book, open textbook. You do whatever you want, but do not cheat, because again, as your TA warned you, if we find that you have cheated, or if we find that I just get a hint that there is some chat, and it's very easy to do that, trust me. And you're sharing answers, so that would be the end of it for you. Okay, I will report you to the school, and then whatever decision they make is up to them. All right, because I do not tolerate any cheating. Don't cheat yourself. Study, and if you have questions, ask me, email me, and I will answer you. And if you do not know something, try to work it out. It's better to have a wrong answer rather than to have something that is not yours. Okay. Okay. Thank you very much, guys.
Sorry, Professor.
Yes, sir.
Can
we please talk for 2 minutes regarding local minimums now? Sultan, yes, sir. Okay. Your question is regarding the quiz, right?
Not exactly of this subject. As last time we had a quiz on data structures and this subject on 1 week, but will we have the quiz on data structures on the next week? I just forgot about
data structures. Why is data structure? No, we don't have a quiz on data structures. We have a quiz on only numerical. These two courses are different. Do not come. If you're taking 2 courses with me, it doesn't mean that we'll have quizzes at the same time.
Okay.
Because there are many students who do not have that course with me. Okay, you wanted to talk about local minimums now. Sultan,
yes.
Please.
Yeah. I think in the quiz you defined local minimums to be the same as local extremums, but imagine as
okay. Let me clarify that. The quiz
non-zero slope.
Okay. First of all, if I'm telling you a point is a local minimum, then definitely the first derivative of the slope would be horizontal. Okay, it would be 0. Okay, so that's the first test. Okay, so we know that. Now, in the quiz, in the lecture slide, lecture 1, one of the slides, there was a plot where there's a sine function and exponent function. I don't remember exactly. But there were 3 points, and over there at that point of the course, I did not talk about the first derivative or second derivative. I just wanted to visually ask you guys or make you guys understand or help you guys understand what a local minimum or a minimum actually means, okay? Or a local and a global minimum means. I wanted you to compare the minimum points and to understand what's the difference between local and global. So in that function, since we are looking at the positive functional values, at x is equal to 0, if you evaluate that function, you will see that it is not equal. It is not, the slope is not equal to 0, okay? But in this slides, I said that's a minimum point. At that point, yes, that could be considered a minimum point without considering or without taking into account the first derivative and second derivative test, okay? But once we learned about the derivative test, we can go back to that slide and we can say, okay, that point at x is equal to 0 is basically not a local minimum. Okay, and that is because when we do the test, the necessary and sufficient condition test, that gives us the result. Okay, so please do not confuse that. Do not, I think this was a misleading point. In that slide, I've written that there are 3 local minimums. That local minimum is just to tell you that, okay, there are 3 points where we have minimum values, okay, but it doesn't mean that they are local, because if you plot that function to the negative part, you see that definitely that's not a local minimum. So so in that slide, my intention was only to try to help you guys understand the difference between what's the difference between a global minimum point and local minimum point. Okay, is it clear?
Yes, I understand now. Thank you.
Yes, so because at that point I did not tell you, if you look at your slides or you look at my lectures, there was no information about first derivative, second derivative, and slopes. It was just a visual graph where I wanted you guys to understand how to compare or how to actually compensate what is a local and global point in a given function. Okay, probably I shouldn't have used the word minimum. I should have used a local, I don't know, a local, what else could I use? Some point which is in the valley, I wanted to identify. So the point at x is equal to 0 could be considered as a point in the valley because we did not know what is on the negative side of it. Okay, but definitely that point is not a local minimum. Okay, so pardon me if the misunderstanding is due to my explanation, but definitely that was not my intention. So correct it if anyone is made a mistake over there. In that slide, I don't remember the slide number, but in lecture 1, there's a function, an example I've given you, and I've asked you tell me how many local minimum points are there. And I've written 3 local minimum. At x is equal to 0 is one of the local minimum, but basically that is not true. At that point, only visually you can tell me, okay? But analytically, if you work it out, you will see that x is equal to 0 is not a local minimum because the slope is not equal to 0. So what we want to conclude is that if I tell you that a point is a local minimum, then definitely the first derivative will be equal to 0. But if the first derivative of a function at some point is equal to 0, it doesn't mean that, it doesn't imply that that point is definitely a local minimum. It could be a saddle point. Okay?
Okay.
Good.
Thank you.
Thank you. Any more questions? Okay, and also in quiz 1, now that, okay, let me, okay, that's it. So we can stop.